All right, so now we're going to put all the pieces together and talk about the architecture of an entire CPU. And we're actually going to talk about this in two pieces. So in this first piece, we're going to be talking about some of the concepts in general, and then in the second piece, we're going to apply it to particular architecture, specifically the y86 architecture from your textbook. So in this piece, we're going to be talking about CPU stages and design and pipelining. So let's start with the first one. So we know at this point that a CPU consists of combinational circuits, primarily for computation, sequential circuits primarily for remembering things, wires and buses for connectivity between all the components and for storing intermediate results, and then a clocked register program counter, specifically for synchronization and keeping track of where we are in the program. All right, so this is an example from your textbook about how all this works. So the entire process is coordinated by the clock, and you can see the clock ticks here at the top. So clock turns on, off, on, off, on, off, and so forth. And so every one of these on-off cycles is, or every one of these on-off sequences is called a cycle. So the on is the beginning of the cycle, and then the next on is the end of the cycle. Okay, so the diagram here at the bottom shows a high-level overview of what's going on in the CPU at various points in this cycle as the CPU executes this program here. So we're looking at cycle 3 specifically, so the program is about to execute this add instruction after these first two loads. So we are at the beginning of cycle 3, which means we're right here, and the clock tick has just occurred, and we are about to execute cycle 3, which means we're about to execute this instruction. And the program counter, you can see here, is set to the address of that instruction. And that's really what feeds the rest of the CPU. So all the rest of the logic takes that address, reads the instruction from memory, looks at the bytes, and determines what it means, what it needs to do. It reads any values that it needs from memory and the register file, does any computation that it needs to, updates any condition codes, and all of that is happening inside of this combinational logic segment. And it takes a while for that to happen. So these are very extensive circuits. They're very large, and there's a lot going on. And so it takes a while for all of this to converge to the final answer, or whatever the result of the instruction is. And so the hardware is constructed such that it will converge by the beginning of the next clock cycle. And that's why it's really important to have that clock synchronizing everything. So we know that while the clock cycle is going, everything inside of this combinational logic block is in flux and updating. But by the time we get to the beginning of the next clock cycle, which is this part of the diagram right here, so this is right at the end of cycle 3. So we're just about to have the clock have its rising edge going into cycle 4. And we know at that point that all of the combinational logic for cycle 3 has now finished. And in particular for this instruction, since we're adding RDX to RBX, we have a new value for RBX. So that needs to be saved into the register file. And remember that the clocked register inside of the register file has been holding the old version of RBX this whole time so that we could use it as we're running all this combinational logic. But now we have a new value of RBX, and we also have a new value for the program counter that we calculated as part of this combinational logic. So this is what the CPU looks like right as we're about to hit that clock tick to go into cycle 4. And that's really what triggers the transition from that instruction in cycle 3 to the instruction in cycle 4. And here's what the diagram looks like once that happens. So at event 3, we are now on the other side of that clock signal rising. The new value for RBX has now been locked in. The new value for the PC has now been locked in. And now we can begin the whole cycle again with all of the combinational logic updating for cycle 4 rather than cycle 3. And so that'll all happen. It takes a clock cycle to converge. And then when we get to the end, maybe we'll have some new values that need to be loaded in. In this case, we've calculated the new program counter value, so we've decided that we're not going to be taking this branch, and so we're just going to go ahead and execute the next instruction. And so if we were to have a diagram of what happens at the beginning of the next clock cycle, we would see this new PC value being locked in, and then of course the whole thing would start over again. So that's a high-level overview of what happens. Here is the diagram from your textbook about the y86 CPU. So they call this SEQ, S-E-Q, and that's because it's a sequential y86 CPU. It runs only one instruction at a time, just like we've been talking about so far. YSIM, the program on STU that you can use to simulate your y86 programs, that is actually a simulator of this hardware. It's written in a language that allows you to simulate running on actual hardware. So there are a bunch of components. You can see the clocked register for the program counter here at the bottom. Again, that kind of drives everything else. There are a bunch of hardware units that are kind of the things that we've been talking about up to this point. So some of these are combinational, like the ALU. Some of them are sequential, like the register file and memory. So there are just a lot of these components, but all of these are boxes that we can look into, and we have looked into these boxes up to this point. The rest of this is a bunch of control logic, these gray rectangles. We haven't looked at these specifically in our lectures so far, but the details are in your textbook, and they're really just combinational circuits. They're just there to help split up data and combine it in various ways. And again, the details are all there, but the details aren't terribly important for us. And finally, there are a bunch of wires connecting all of these components together, and now we have wires of different thicknesses. So we have 1-bit wires, like this one right here. We have 1-byte wires, like this one right here in the thin lines. And then we've got the word-sized wires, which are drawn using thick lines. Okay, so that's an overview. Now we're going to talk about some other concepts related to CPU architecture, and then, like I said, eventually we will dive into the details of how the y86 CPU works.